So we were looking at the hydrogen deficiency index or the index of hydrogen deficiency or some form of unsaturation from the molecular structure. If you are given the molecular structure, how are you going to calculate or count your HDI or degree of unsaturation? And we figured out you will just count your pi bonds or if any rings are present. In case of a double bond, you will count them as one pi bond, but in case of a triple bond, you must count 2 pi bonds. In case of a ring, you must count that as 1 degree of unsaturation. The next thing about HDI is when you calculate it using a molecular or actually a formula. So HDI from molecular formula. And this is where a formula of your, on slide number 5, will come into help you. This is the formula that all of you must memorize. 2 times the number of carbon plus the number of nitrogens. So all the multivalent atoms, the carbon and the nitrogen, have to be added. Minus the number of hydrogens and minus the number of halogens. Oxygens and other divalent atoms, we don't need to count those. And then you will add a +2. So if you look at my screen now, my page now, HDI or IHD can be calculated by 2 carbons. Twice the number of carbons there are, the number of nitrogens there are, minus the number of hydrogens, minus the number of halogens. And if we put it in the parentheses, add a 2, make a bigger bracket, then divide by 2. All of this. Okay, so this would be a better representation of this formula than the formula that we looked at our slide. So if you look at this slide, and if you were just given the molecular structure, there is a ring here, nothing else, no other pi bonds. So HDI for this molecule is calculated as 1. For C3H5Br, the HDI has to be calculated as 1. So let me write this down, H3H5Br. Following this formula, I will do this. Twice the number of carbons. So I have 3 carbons plus the number of nitrogens. There are no nitrogens right here. So I don't have to add any nitrogens. Minus the number of hydrogens. There are 5 hydrogens. Minus the number of halogens. There is 1 halogen. Oh, I forgot to add the 2. So I have to add this 2. And this is something that most of the students also do. They forget to add this 2. So 2 times 3 is 6 minus 6 plus 2. So 0 plus 2, 2 divided by 2 is 1. So the HDI for this particular molecular formula has to be 1. In the upcoming isomer quiz and in your exam and in your drill test, you will see that I will give you molecular formula and I will ask you to draw constitutional isomers from this part. And so you have to remember, whenever you are asked to draw constitutional isomers, you will first always calculate its HDI. What will HDI do for you? The HDI will help you figure out a reasonable framework of the structure. So for example, the HDI here was 1. What is a reasonable framework for this particular structure? There is either a pi bond or a ring present in this molecule. Now remember, ring can only be present in an atom or in a structure which will have more than 2 entities, especially the multivalent ones, either the oxygen or a nitrogen or a carbon. So more than 2 of those are needed. Hydrogens and bromine, they cannot be added between any 2 elements. This is wrong. Hydrogens and halogens make only 1 bond. Always remember that. So with that in mind, that we either are going to have a pi bond or we are going to have a ring, let me draw the smallest ring possible first. So I'm going to write it in a triangular shape. And then what is the next thing that I do? Draw the multivalent atom first. And then I've drawn all that. What is my next multivalent atom? There are no other. Now I'm going to just fill in my univalent atoms. Do you all understand what a multivalent and a univalent atom is? Multivalent is when you have multiple bonds that can form. For example, carbon can form 4 bonds. Any atom which can form more than 1 bond is a multivalent atom. So to this carbon, how many bonds are already attached? 1 and a 2. So I'm going to put 2 more hydrogens here. To this carbon, how many bonds are already attached? 1 and a 2. And so I'm going to add, yes, 2 more hydrogens.
I'm sorry, it was a multivalent and what was the other one?
Univalent. Univalent, and then there's divalent, trivalent. Most of these are known just as multivalent. You know, di, tri, tetra. Uni is 1, di is 2, tri is 3, tetra is 4.
Okay, thank you.
You're welcome. So to this carbon, how many bonds are attached? 1 and a 2. But now I cannot just add 2 hydrogens. Let me just write it for a few minutes. Then where will my bromine go? So I'm like, what did I do wrong? And so I will count all my atoms. Always check back. I have 3 carbons. Yes, I do have 3 carbons. I have 5 hydrogens. I have 1, 2, 3, 4, 5. What? No, I can't have more than 5 hydrogens. What should be replaced by this 6th hydrogen? The bromine. And is this a reasonable structure? Yes, it is. All the carbons have their 4 bonds. All the hydrogens have their single bonds. All the halogens have their single bonds. This was a net neutral molecule, and this is also a net neutral molecule. So I check back and everything looks in place. This is one of the constitutional isomers. What is the other constitutional isomer I could have? I can have a pi bond. Do you think I can have a pi bond within this structure?
No.
No. So I will have to draw a linear structure. And now I will give my double bond or pi bond. So this is the first bond that forms between 2 atoms is a sigma bond. The second atom, the second bond that forms between the same two atoms is a pi bond. So I draw my multivalent atoms first. I have assigned my pi bond. Now I'm going to fill in with 5 hydrogens and 1 bromine. Now hydrogens I can fill in anywhere. Where should I put my bromine? I have several choices now. And let me just draw what I will be planning to do. These are the 2 carbons who are involving the pi bond. And this is the allylic carbon. What is an allylic carbon or allylic site? Allylic site is a third atom from the pi bond. So there is 2 of these atoms and then there is this third atom. That is your allylic site. In this particular case, we do have an allylic site. Now I can put my bromine on carbon number 1. I can put my bromine on carbon number 2, or I can put my bromine on the carbon number 3 or the allylic site here. Are you all with me so far? And then I will now fill in the rest of my hydrogens. This carbon is already making 4 bonds. I don't have to add in any other hydrogens here. But I will have to add in 3 hydrogens here because this carbon was only making 1 bond. This carbon was making 2 bonds, so I gave it 2 hydrogens. Let's always check back. 3 carbons, yes. 1, 2, 3, 4, 5 hydrogens, yes. 1 bromine, yes. What about this? 1 bromine, yes. 3 carbons, yes. 5 hydrogens, yes. Similarly, 3 carbons, 1 bromine, 1, 2, 3, 4, 5 hydrogens. So by changing the position of the Br on this or in relation to this pi bond, different connectivity, I have created other constitutional isomers as well. Usually for your exam or on your drill test, I will give you a molecular formula and I will ask you to draw at least 2 constitutional isomers. And you can draw any of these or 3 constitutional isomers, or I may ask among the following, which is the constitutional isomer for this particular compound. Okay? So always do your HDI formula calculation. Okay? So first, when you will do the HDI, figure out your reasonable framework. Draw your carbon skeleton by writing out the multivalent atom first. Before you fill in, I should write this here. Fill the hydrogens at end. Okay, so hydrogens can be filled in later. You don't have to fill them exactly at the same time. I want all of you to use this formula and calculate the HDI for this particular molecule. Use this formula. And what else? A and B. Anybody who has figured out the HDI for the structure A? Any volunteers?
Yes.
Okay, go ahead, Sammy.
We have to multiply 2 by multiply 6 for carbon plus 1 for nitrogen
Very good.
minus 8 for hydrogen
Yes.
and 1 for bromine. 1 and 2 it's 3 minus 3
Yes. Yes.
and oxygen, don't worry about it,
Yes.
plus 2
Yes.
divided by 2.
Exactly. Very good. And so what would be the answer for this?
12, 13 minus 11. So it's 2.
It is 2. Do you all understand this? 12 plus 1 is 13. Minus 3 is 10. Minus 8 will be 2. 2 plus 2 is 4. 4 divided by 2 will be 2. So you know the HDI. Do you have a reasonable idea now what could be the structure here? Definitely a ring or a pi bond can be present, or
One ring.
both. Or
One
both
ring
can be
after.
present.
Mhm.
So I'm going to draw a linear structure first. 1, 2, 3, 4, 5, 6. And I will also draw a ring structure. So if I draw a ring structure, how many HDI I have already used? Out of the 2 HDI, I have already used 1. So I can certainly provide 1 pi bond also. So 1 pi bond and 1 ring will give me what HDI? 2. Whereas for this linear structure, I will have to make sure that I give at least 2 pi bonds. Now for my linear structure, I gave my pi bonds between C2, C3, and C4, C5. Anyone who did not understand this part? Iana Hayward, are you here? Is that how you call your name, Iana?
It's Ayana.
Ayana? I'm sorry, could you repeat that?
Yes, it's Ayana.
Ayana. Okay, Ayana, did you understand what I just did?
No, I'm actually kind of confused.
Okay, good. Tell me. I'm glad I pointed out to you then. Go ahead.
I get how you did the numbers, but I guess it's just the structure of how you're drawing it. I'm confused.
Oh, these up and down hill and valleys.
Yes.
Okay. Would it make you feel better if I write it like this? 1, 2, 3, 4, 5, 6. Would this make you feel better? The square version?
Yes. But if it's
Okay.
supposed to be drawn like the first part, or it doesn't matter?
So eventually, after your second module, this will not be allowed. This would be the proper way we will be drawing our structures. And I'll explain to you in a few minutes why we draw it like this. But do you understand why did I draw where are these pi bonds? That's what I was concerned with. Do you understand that?
Let me see.
Because in my second structure, I'm going to change the location of these pi bonds relative to each other. In my first structure, I will be drawing them between C2 and C3 and between C4 and C5. You see that?
Yes.
And in my second structure, I have drawn them between 1 and 2, carbon 1 and 2, and carbon 4 and 5.
Okay.
What about these two guys? They have same molecular form. Well, I didn't draw in the rest of these, but they have the same framework, but different locations of my pi bond. So if I fill in these correct, the nitrogens, the halogens, and the oxygens correctly here, I can say that these two are constitutional isomers. So the location of pi bonds can also act as your or help you create more constitutional isomers. Do you see that, Ayana?
Yes, it makes more sense now.
Okay, very good. So this is something that I want all of you to remember, because sometimes my students tell me later when the quiz is over or the test is over that they didn't know that they could move the hydrogens or the double bonds also. So there is a bromine and a chlorine. I can put the bromine and chlorine on the double bond. I can put my, and don't worry about this structure that I'm making now. I can put both chlorines on my double bond. Don't you think these will again become constitutional isomers if I put my bromine somewhere else, like on the allylic position? So I can make several constitutional isomers by just moving these double bonds, by placing different groups on my double bonds also. Okay, I want you all by today, because we will have our module 1 test tomorrow during the drill class. Why don't you practice drawing constitutional isomers, as many as possible, for this structure? Okay, do you all understand what I just said? So for structure A, draw as many constitutional isomers as possible. Okay. Now, what about this structure B? Anyone else other than Sammy and Ayana who would volunteer to do this? HDI? Is there anyone who I did not count? Larion Clausel. Is that how you say your name, Larion?
Yes.
All right, Larion, can you help me do this? And when I call out your name, please don't feel offensive about it. I know you're taking the stab for the entire class. So everybody should probably get you something nice, a chocolate or a coffee, whatever you like. But don't take it offensively. I just want all of you to be involved, and I want to make sure that everybody is in the class at the same page. Okay? Can you help me solve for this, Larion?
Yeah. So it's 2 times 3
Very good. Mm-hmm.
minus 6
Very good.
minus 2
Very good. And then,
plus 2.
very good.
And then divide it all by 2.
Yes, good. And how we solve it?
Oh, 6 minus 6, 0.
Mm-hmm.
So 0 over 2. So 0.
Mm-hmm.
It's 0.
Exactly. So for this particular structure, can you suggest a framework, Larion? Will there be pi bonds? Will there be a ring? Or will it be just a linear, regular linear structure?
Just a linear structure.
It will be a just regular linear structure. I will draw my 3 carbons. I will first put in my bromine and chlorine. Let me put my bromine here at carbon 1 and chlorine at carbon 3. Okay. Take a new page. So I'm going to copy a little bit from here. C3H6BrCl. So I have my 3 carbons. I'm going to place bromine on one, chlorine on the other. 1, 2, 3. Okay, thanks, Larian. You're off the hook for now. Taylor, can you help me with this? Taylor,
Yes.
Okay, good. Tell me, Taylor, is structure A and structure B constitutional isomers, different structures, or same structures?
Same structure.
Exactly. Very good, Taylor. What I did here was I just switched the locations. Instead of counting this as 1, I'm going to count this as 1. And I'll tell you eventually why we count bromine 1 as a 1 and why this has 2. But this is just like a mirror image of this particular structure. So both of them are exactly same structures. So structure B is not a constitutional isomer of A. However, instead of 3, if I had my chlorine at the second location, now A and B are constitutional isomers. Does everybody understand this part? Any questions from this part? Yes, go ahead. Oh.
Can you repeat why they'd be constitutional isomers if you move the chlorine?
Because in the structure A, bromine was on carbon 1. Chlorine was on carbon 3. Now the connectivity is a little different. Bromine is still on carbon 1, but instead of being at 3, chlorine is now on carbon 2. So this slight connectivity difference also will make these two constitutional isomers. Does that answer your question?
Yes, thank you.
Okay, you're welcome. And now I'm going to put my bromine and Cl on the same carbon. Okay, and then we fill in our hydrogens. So C and D, A, B, C, D, all of them are constitutional isomers. What about this one? E. Is this a new constitutional isomer or something that we've already seen?
We've already seen.
Exactly. E and C, they are exactly the same structures. On the same carbon, we have both the bromine and chlorine. Very good. Now, once you are good with HDI and constitutional isomers, there's another formula that all of you will have to memorize. These are known as formal charges. Eventually, down the lane, you will not have to calculate this formula. You will just look up in your periodic table and you can figure out if you are going to have a +1 or a +2 or what. But let me show you our, oops. Slide 14, I think. So formal charges. Formal charges help us figure out how many electrons an atom has in its possession. And there are different kinds of formulas that there are available. But what I would like all of you to know is that formal charge is calculated by valence electron of an atom in its neutral state minus the shared or the bonding electrons, the atom in that structure divided by a 2. And all of this has to be subtracted by the unshared electrons of the atom in the structure. What does that even mean? So if you look at the screen, I have a CH3 and a O. Okay, let's figure out the formal charge on our O. And I'm going to draw the Lewis dot structure. So this is the structure that we have. In other words, or in other representation, as I would say, the oxygen has its 2 lone pairs also, and it has an extra lone pair on it. But how are we going to figure out what is the formal charge of oxygen? So
Excuse me,
yes.
could
go
you
ahead,
stop
please.
sharing your screen to see?
Oh, I'm
Yes.
sorry. I'm
Oh,
sorry. Yes,
no problem.
yes. Thank you.
Okay.
Thank you for reminding me. I forgot about that. Okay. So all of you have this formula down. Valence electrons in neutral atom. So how many valence electrons are there in oxygen when it is in its neutral state? 6.
6.
Right? In its neutral state. We are not worried about the structure. In this structure, how many shared or bonding electrons oxygen have with the rest of the structure?
2.
So only 2. 2 divided by 2. And how many unshared electrons this oxygen has in the structure? 6. And if you do the math, this will become 1. 6 minus 1 is 5. 5 minus 6 will become minus 1. Now this is very reasonable. Why is it reasonable? Oxygen, and if I show you our periodic table again, oxygen can make only 2 bonds. Oxygen wants to make 2 bonds, so it will feel complete. Its octet will be complete. If it makes 3 bonds, where is the third bond forming with? It is forming the third bond with its one of the lone pairs. So it is losing one of its lone pairs to make a positive charge. But in this particular case, instead of making 2 bonds, oxygen is making only 1 bond. What does that mean? It still has an excess of electron on it. I'm sorry. I don't know what this is. So this oxygen, instead of making 2 bonds, is only making 1 bond. And what is the extra electron doing? It is giving the excess charge to it. Now, on the other hand, let's look at this particular structure. And let me make the dot structure again here. What will be the formal charge for this particular structure? What is the valence electron in neutral oxygen? 6. How many are sharing electrons in the structure? 6. And how many unshared electrons? Right? So if we solve for this, 6 minus 3 is 3. 3 minus 2 is a 1. We don't write just 1. We write it as a plus 1. So whenever oxygen will have to make an extra bond, it will have to lose its lone pair electrons. When you lose electrons, you become positive. When you have excess of electrons, you become negative. How many electrons are being lost? That's the number we write here. Any questions from this part? Everybody understood everything? All right, let's do a sample problem here. I want you to tell me what is the formal charge on nitrogen. Can you all see my structure?
5.
I'm sorry, formal charge, not valence electrons.
3. Oh. Here in this structure?
In this nitrogen, on this structure, what is the formal charge on nitrogen?
1.
Okay. Can you show, can you help me solve for it?
2 for H.
Okay, so nitrogen has how many valence electrons?
5.
5.
This will be minus 1 because this is 2H and the double bond with carbon and the 1 lone pair. So
There
it
is
would
no
be
lone pair.
Oh, I'm confused.
So the
Okay.
5 valence electrons for nitrogen. How many shared electrons are here for nitrogen? 2,
8.
3, 4, 5, 6, 7, 8. Who is not with me so far? Don't be shy. This is the time that you ask these questions. So 8 shared electrons divided by 2. And then how many unshared electrons do you see on nitrogen? There are none. You know why? Because that lone pair, nitrogen has given away to form the 4th bond. Nitrogen makes how many bonds usually? 3. But in this case, nitrogen is making 4 bonds. It has lost its lone pair electrons to make the 4th bond. So there are no more unshared electrons left here. So 5 minus 4
Is
is
1.
a 1. And we write a plus 1. So in general, what do you observe? Whenever an atom will be making less bonds than it needs to, it will get a negative charge. But if it will make more bonds than it needs to, it will get a positive charge. Carbon is a very special atom. It will never have more than 4 bonds. Look at this structure. How many bonds nitrogen is making here? 2. So it is making less bonds than it needs to. Nitrogen makes 3 bonds. But today, or sorry, in this structure, it is making only 2 bonds. So it has those excess electrons on it. So if you don't even know this formula, can you figure out what would be the formal charge on this? -1. Why? Because it has those excess electrons on it. So if you want, we can do the solution here. And I'm writing it in my paper. All of you also try to write it on your paper. Nitrogen has 5 valence electrons. How many sharing or bonding electrons it has right now? 1, 2, 3, 4. So 4 divided by 2. How many unshared electrons it has? Because we see the negative charge, we know it has to be 2. Otherwise also the structure will have something like this. Two or -1. Okay. So please make sure that you all know how to calculate HDI, how to calculate formal charges. Now, besides these formal charges and complete octets, there are few exceptions to the octet that all of us need to know. Borane and aluminum, these are atoms with 6 valence electrons. Usually in the second row, how many electrons make the valence electrons for the second row atoms? 8. But borane and aluminum, these are special elements which can be happy with their 6 valence electrons also. And you will see down the lane that these are electron deficient atoms. Electron deficient or Lewis acids. By Monday, we will start our module 3. I would want all of you to not waste your weekend and study about your acids and bases during this weekend. I know you'll be preparing for your module 2 also, for the drill test of module 2 also, but knowing your acid bases, knowing why any moiety or anything acts as an acid or why anything acts as a base is very important and critical for this organic course. Similarly, phosphorus and sulfur, even though they are in row 3, they can expand their octet. They can go to, from 3p, they can go to 3d orbitals. And that's why these 4 elements will show you exceptions to the octet rule. Again, I'm reminding you and I want to emphasize to please remember that these 2 elements will be giving rise to several Lewis acids that you are going to do. Okay, so mark this or put a big star and make the light come out of it or whatever you want to do. Okay. The last part of our module 1 is about hybridizations. Now, there is a lot of information available to our in our content, in our Klein, and in our slides also. But what I will be skipping a lot is the physics and the math behind it. For hybridization, we will only focus mostly on the structure and the shape, followed by bond lengths and strengths. these are the most important concepts that we need to know about from hybridizations. Now, all atoms are bonded to other atoms based on the valence electrons available to them, right? And if you know, in an atom, we have what is known as the atomic orbitals. So that's what the electrons fill up. Let's say carbon, right? Carbon has 6 electrons in all. If you think about the atomic orbitals that carbon has, it has 1s orbital, then the 2s atomic orbital, and the 2p orbitals are on the same level, right? So these are the atomic orbitals. And by all the filling in principles, the first level is filled in first. And we point these electrons, there are 2 electrons with different spins. So the first orbital is filled in first, making sure that the pair is there. Then the second orbital starts to get filled. Before it goes to the other, depending on our energy of the atomic orbitals, the 2s orbital will be filled in first. And so how many are left? 2 more are left. So these are the atomic orbitals. So in an atom or in a special atom, electrons fill the atomic orbitals of the atom. But we will be dealing with molecules. What are molecules? Molecules are atoms or group of atoms, different group of atoms who combine together and make new molecule. In molecules, we get hybridization. The orbitals hybridized or blend in to make new orbitals. So for example, if we have a carbon atom and we have a hydrogen atom, the hydrogen atom has only 1 electron in the 1s state. So this is the 1s state of hydrogen. This is the 1s state of carbon. None of these are going to react. Which is going to react? 2p part is going to share its electrons with hydrogen. But in molecules, fortunately, a blending of the s orbital of hydrogen and the p orbitals of carbon will take place, causing molecular orbitals to occur. Now there's a word that I want all of you to know, degenerate. Degenerate means same level or something very similar to that. We say degenerate levels and degenerate energies also. Why do we say that? What happens in carbon is the s orbital and the p orbital become degenerate. So I'm going to I'm not going to redraw this. One of these electrons get promoted to the p. So this is your p. And this 2s is left behind. But then when one gets promoted, generate. All of these are on the same level. How many hydrogens come and fill these orbitals up? These molecular orbitals up will define how many bonds that carbon will have. So again, how many bonds a carbon can make? 1, 2, 3, 4. 1, 2, 3, 4. So all these red are electrons from other atoms. Any questions so far? So this is the degeneration of your sp3 orbitals. Okay. Each of this orbital has 1/4 s character and 3/4 p character. And that's very reasonable, right? Because there is 1 part s, 3 parts p. If I have 100%, 75% will be p, 25% is s. Does this make sense? So 1/4 part is s orbital, while 3/4 part is the p orbitals. So in a regular hydrocarbon, you look at carbon or the central atom, and then you see how many electron domains or effective pairing that can occur here. In this particular example, 4 effective pairings can occur. And so we say that this will be a sp3 hybridized atom. Right? So hybridization is just a modification of the electron model, and it can adjust to make itself more comfortable. And we'll see that. Very quickly, I'm going to go over this. This was sp3 hybridized. There are 4 domains or electron densities or effective pairings, as you call them. So 4 indicates sp3. 3 plus 1, 4. However, when you will see multiple bonds forming, the sigma and the pi bond forming, there will be 3 sp2. So the 1 part s and 2 parts p. So sp2 out of the 100%, 66% p and 33% s. On the other hand, when you have a triple bond, there are only 2 pairings possible. And so we have a sp2, sp hybridization. So out of that 100%, 50% is p, 50% is s. As our effective domains or electron densities change, the s character in the atom increases. How is this helpful? The s is a spherical kind of a orbital, whereas your p is a dumbbell kind of a orbital. Whenever your hybridization is occurring, so let's say that this is your sp3. So I'm trying to make a 3-dimensional p orbitals. And then there is this s. When this sp3 hybridized carbon will bond with the s orbital of a hydrogen, these s are going to overlap first. Do you understand what an overlap is? So let's say that this is my s orbital of one, this is the s orbital of the other, and they will overlap on each other. The more the overlap, the better the bond between them will be. So if I'm drawing a molecule like this, how many bonds this carbon has? 1, 2, 3, 4. So it has 4 electron densities or domains around it. What is the hybridization associated with it? This has sp, so 2 domains. This has sp2, so 3 domains. This has sp3, so 4 domains or 4 electron densities. So this carbon is sp3 hybridized. What about this hydrogen? This hydrogen is only S because it is just an atom. This carbon, on the other hand, hybridized itself or blended or modified itself to make adjustments. So instead of just getting 2 bonds, carbon makes 4 bonds. And that is why carbon is so special for making organic materials. No other atom is able to accommodate 4 groups around it so comfortably. Okay. Let me show you my screen now. So how does this hybridization affect our geometry? And you know what? I'll make our own table here. This is a table that you will see in several of our books also. But this is what I wanted to explain to you. Let's say that we have an example here and the electron densities or electron domains, okay, effective pairings, or steric number. So this number can be known by different values. Hybridization, angle, atomic geometry, and molecular geometry. And I'll explain to you what is an atomic geometry and what is a molecular geometry. Now, our basic very first example is CH4. And we just saw here carbon has these 4 bonds. CH4. Okay. So before you draw CH4, you have to think everything about your Lewis structure, about your HDI, right? All that. You have to think about it before you draw this CH4. So how many electron densities are around CH4? There are 4, or the steric number is 4. So what is the hybridization associated with 4? sp3. Now what I'm going to explain to you next is a little different from what you have studied so far. We have been drawing this square rectangle. And Ayana, I hope this will shed more light on what I'm going to say. But the bond angle between all these hydrogens is not 90 degrees. It is arranged in a manner that all the atoms are farthest away from this carbon, making a tetrahedral shape. So what do you see here? You see that 2 valleys or 2 V's, inverted V's are present here. One of the bond is coming out and the other bond, the 4th bond, is going at the back. This is the structure of a carbon. Now, Wish I had my model with me. So I have these two V's and I insert one V into the other. This is a tetrahedral structure. Two V's inserted into each other. Any questions what I showed you right now? Anyone? Okay. So in a tetrahedral structure, the bond angle is 109.5 degrees. Because there is no lone pair present, the molecular geometry will also be tetrahedral. Now, why did I say about the lone pair? Let's look at ammonia. So ammonia, if I draw my Lewis structure, what do I see? Elizabeth, chat. Okay, I can't see your complete name. Elizabeth Chapman. Okay. Hannah Young, are you here? Hannah Young, are you here? Okay. Okay, any volunteers for this structure, for this question?
Okay.
Okay, thanks, Sammy. How many electron densities do you see around nitrogen?
4.
Okay, very good. When you have 4 electron densities, what has to be the hybridization involved?
sp3.
sp3. The bond angle will be 109
9 tetrahedral.
and the atomic geometry will also be the same, tetrahedral. But the molecular geometry is not this square. I'm going to redraw my tetrahedral structure here. So the basic bottom part is the same. And my lone pair will occupy the 4th location. But when I will look, I will see only this trigonal
pyramid.
So instead of doing tetrahedral molecular geometry, NH3, which is 3 plus 1 lone pair, gives me a trigonal
pyramid.
Very good. Thank you, Sammy.
Welcome.
Excuse me.
Go ahead.
Do you have any tips on how to remember how to draw these structures?
So first, practice a lot, first of all. Look at my drawing the structure, and then you also draw the structure exactly same. So for example, I drew this nitrogen, and then I drew a V. That was the first thing I drew. I just said that a tetrahedral are 2 V's inserted into each other. And you can use models also, you know, in our syllabus, I have mentioned the models that you can use. You will have to draw these structures, and I hope all of you are drawing these as I'm drawing these. You don't have to write all the words that I'm writing, but you must draw your structures, all your structures, all the chemical reactions. You must be drawing along me. Do you want me to see your paper right now? What you drew?
No, I was just needing tips on, I was trying to see if you had any tips on drawing them.
Well, this is my tip. You have to draw them or probably trace them on some paper that has the right kind of structure. Let's look at another example, H2O. So again, remembering your Lewis structure and your HDI, the OH looks like this. So again, how many electron densities I have around this oxygen? Four. Very good. 4. And now I have 2 bonding, but 2 lone pairs. So how will I draw this? I'm going to draw my tetrahedral structure first. Instead of drawing my lone pair, I'm just going to draw my dashed line. And then one goes up. How would I see this in an X-ray crystallography? I will not see any lone pairs in my X-ray. All I will see is a bent structure. So this is still sp3.
sp3.
Angle is still 109. Atomic geometry is still tetrahedral. But the molecular geometry is now bent. Very good. Very good. Now let's look at an example of C2H4. When I draw this C2H4, how am I going to use my Lewis structure and HDI to know what is this first structure? Remember HDI, C2H4. Who can tell me what is the HDI of this particular compound?
0.
We just did this.
Sorry, yes. 1.
Very good. So there are 2 carbons, 2 times 2. There are no nitrogens, but there are 2 hydrogens. Plus 2 divided by 2. So 4 minus 2 plus 2. You will get 1.
No.
Okay, hold on. 4
2.
minus 2 is 2. 2 plus 2 is 4. 4 divided by 2.
It's
Did I
2.
do something wrong? C2H6. I'm sorry.
Yeah.
This is C2H6. I did not write this number right. Minus 4 plus 2. So this is C2H4. I did not write a 4 here. I wrote 2 here.
It's 1.
And so now this is 1. What does this indicate? I will either have a pi bond or I will have a ring. However, with 2 carbons, I cannot have a ring. What I will have is a pi bond. And now I will just fill in my hydrogens. And don't worry, I'm not writing the correct structure. I'm just still drawing the square thing. However, when in real time, the carbon is placed with 3 different atoms around it, it will want to be at the maximum distance from all of them. And so when you have 3 electron densities,
sp2
you will have, no, the bond angle
on angle 120.
is going to be 120. Now, having a bond angle of 120 will help the 3 atoms or 3 electron densities or electron domains to be at the farthest distance. And hence, the structure that will generate because of these 3 domains is known as the trigonal planar structure. Okay. So how many domains do I have? I have 1, 2, 3. With 3 domains, with 3 domains, my hybridization
sp2
is sp2. And what is my bond angle? My
120.
bond angle is 120. What is my atomic geometry? Trigonal planar. And for this particular compound where I don't even have any lone pairs, there will be no hidden bent or pyramidals. It will still be trigonal planar. Any questions? Who does not understand this?
I have a question.
Go ahead.
So would you say that, okay, so the atomic geometry and the molecular geometry are the same unless there's like lone pairs and then it changes the shape?
Yes, yes, yes. That's right, Dahazia. And how about you help me with the next structure? And don't worry, don't be scared. I will help you. Dahazia Hopkins, right? That's so let's do HNO. So CH3NO. I know it's a little over, but I'm helping you practice your Lewis structures also, right? So for CH3NO Dahazia, how are we going to go about? What is the first thing that we should do?
Calculate the HDI.
Very good. So what is the HDI here? And do you want me to show you the formula?
It is about 2 times 1.
You can unmute yourself while you're thinking aloud. It'll help others also see how you're thinking.
Okay, so it'd be 2 times 1 plus 1 for the nitrogen, minus 3 for the hydrogens.
Very good. Nothing about the oxygen.
Nothing about the oxygen, yeah.
And then?
The plus 2.
Very good.
Then you divide it by 2. So I think it's 2, 3, 0, 2, 1.
It is 1. Very good. So the HDI is 1. In this particular structure, I only have 2 multivalent, actually 3 multivalent atoms. But there could be a ring or a pi bond, right? Let me give you a hint. The structure that I'm looking for does not have a ring. Even if you make a ring of these 3, right? We will not be able to complete our hybridizations. In this particular set, and in this particular structure. Okay, so these are the two constitutional isomers. The one that I asked you to make, the CH3NO, looks like this. Okay, so these are the two constitutional isomers of this particular molecular formula. Okay, very good, Dihaja. So looking at this structure,
So you want our Lewis structure to look like that, like you ate
So,
three?
so when you draw your Lewis structures, when the questions will be about Lewis structures, you can draw this. You don't have to worry about this actual structure at that point. But after module 2, you will probably not be asked Lewis structures anymore, not in your drill test. And at that point, you will be drawing the hills and valleys to depict the correct tetrahedral structure. Does that answer your question?
Yes, thank you.
Okay, very good. And so this trigonal planar, how many electron domains do you see here? 1, 2, 3. And so 3 domains. However, when we will look in the electronic, and I'm going to draw the trigonal pyramidal structure here. When we will look in the electron diffraction or the X-ray machine, we will not be able to see our lone pair. We will only see this bent structure. 2 plus 1 lone pair, sp2, 120-degree, trigonal planar atomic geometry, but molecular geometry will be bent. C2H2, I want all of you to do this on your own when you have, what will be the Lewis structure of this C2H2. I'm going to quickly tell you that the C2H2 will be something like this. If you have to figure out the hybridization of this carbon, you will have 2 electron densities and the hybridization will be
SP.
sp. For this carbon to have a best location of atoms around it, the bond angle should be 180 degree, which should be linear
Linear.
and linear. Okay. Now, based on the hybridizations, once you know what your hybridizations are, you will be able to figure out among the given structure which, I should have written it this way, which of the carbon-hydrogen bonds will be the shortest, which of the carbon-carbon bonds will be shortest, which of the bonds will be strongest. Okay. Now this will depend on several things. The bond length depends upon number % of S hybridization. First of all, more % S means shorter bond length. What does that mean? If you look at both of these carbons, this is sp3, this is sp3. This is sp2, this is also sp2. This is sp3. So if you look at all these bonds, A, B, C, the single bond, this will be the shortest bond. Okay. Smaller atoms also make short bonds. Now, why is this important for us? If you have a structure like this, let's say I have a structure like this. This carbon hydrogen bond is 1.06 angstrom. You don't have to remember the numbers. What I want you to know is which will be the shorter one. Why is this a short bond? This is attached to a, oops, my bad, this is not sp3, this is just sp. This is a sp carbon. It is pulling the orbitals close to itself very tightly. So this s orbital gets pulled in towards this sp very closely. Whereas to this sp3, where the s character is less, this hydrogen or this hydrogen or this hydrogen is not that strongly pulled in. So a sp3s bond is 1.10 angstrom long, whereas this sps will have less bond length. Do you understand this? Any questions on this? Anyone? Any questions? So my question to you is, if I have a sp3h, if I have a sp2ch, and if I have a sp3ch, A, B, C, who will be the shortest CH bond?
A.
A is the shortest carbon hydrogen bond, followed by this, followed by this. If this is the shortest bond, who will be the strongest bond?
Same A.
Yes, shortest and strongest. Now this is a CH bond. You should also know what will be carbon-carbon hydrogen bonds. So for example, if I ask you which is the shortest single bond in this structure. So this is a single bond between carbon-carbon. This is a single bond between carbon-carbon. This is also a single bond between carbon-carbon. Among all of these three carbon-carbon single bonds, which of these will be the shortest?
A.
It will be A. Can Salome Blackwell,
Yes, ma'am.
can you tell me why?
It's the shortest.
Why is this the shortest? Yes.
Due to it being connected to the that specific C, yeah.
Yes. So the more S character is in the atom between those two bonds. So this is still a sp3 carbon. This is a sp3 carbon bond. This is a sp3 carbon bond. This is a sp3 carbon bond. In A, the S character is more. So there are 1:1 ratio almost. So the more S character there will be, the shorter that bond will be, the stronger that bond will be. Okay. Can anybody tell me how many sigma bonds are here? So you count only one sigma bond at this triple bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 sigma bonds. How many pi bonds are there? Only 2. Let's look at carbon dioxide. I want all of you to take a look at carbon dioxide, calculate its HDI, and come up with a probable structure within the next 1 minute. And today we do not have any drill. So after the class, we just have office hours at 2:40. So I just want a couple more minutes so we can finish up with this module today. Kathy, are you here?
Yes.
Kathy Tran? Okay. Did you get to calculate the HDI of this molecule?
Yes.
Okay, very good.
So I did 2 times 1
Mm-hmm.
plus 2.
Mm-hmm. So there is no hydrogens, no oxygen. Okay, so you are doing the +2 for
Yeah.
the last. Yes, very good. And then,
By 2.
yes,
And I got the HDI to be 2.
yes, very good. So what is the first thing that you will do to draw the Lewis structure of carbon dioxide?
To choose the multivalent.
Very good, very good. So this carbon, I'm going to draw my multivalent atom first, right? And then what would I do? I will place the oxygens around it. And then, so Kathy, I just have one last question for you. Do you think there will be any lone pairs on carbon, or is it satisfied? Is it,
I think it's satisfied.
it is satisfied, very good. So the last thing that we will do today is I'm going to give you this poll question. All of you, can you see the poll question? All you have to do is looking at this Lewis structure, which Kathy helped us see. I want all of you to tell me what is the molecular geometry of carbon dioxide. Now remember, on your drill tests, you can see atomic geometries and molecular geometries both. And don't worry, even if you say this answer wrong, I will count your participation points. There's no wrong answer for Paul. It just helps me see what are you thinking or how you're thinking. Most of the class general.
Excuse me,
Yes.
where will you be posting the picture of your note?
Oh, so today under the lecture, in the lecture section only, yes.
Okay, thank you.
Yeah, I just wanted to finish up all the pages before I put the picture. Yes, but I will. Thank you for reminding me.
Thank you.
If you have answered in the poll, and I see 14 of you have answered. I'm going to end the poll now. And so the answer, 10 of the 14 students have, can you all see the answer? Can you see the view?
Yes, yes.
Okay, thank you. So most of you have chosen the linear, and that is the correct answer. Because if you look at this carbon, how many electron domains do I see around it? 1, 2. And so with 2 electron domains, my hybridization has to be sp with 180-degree angle. Both my atomic geometry and my molecular geometry will be linear. Okay, so this is the end of our module 1.